Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The mid-19th century presented a scientific landscape ripe with both profound discoveries and perplexing enigmas. Understanding the behavior of fluids, for instance, remained a significant hurdle. While the fundamental principles of hydrostatics were well established, a comprehensive grasp of fluid dynamics, particularly the effects of viscosity, proved elusive. Existing models often failed to accurately predict the resistance encountered by objects moving through liquids or gases, leaving engineers and physicists grappling with discrepancies between theory and observation. Similarly, the field of optics wrestled with the complexities of wave propagation. Phenomena such as diffraction and interference were gradually yielding to mathematical analysis, yet the underlying nature of light itself remained a subject of intense debate, with competing wave and particle theories vying for acceptance. The curious phenomenon of fluorescence, where certain substances absorb light at one wavelength and emit it at a different, longer wavelength, presented another puzzle. The precise mechanisms governing this transformation of light energy were far from clear, hindering both theoretical understanding and potential applications. Into this arena of scientific challenges stepped George Gabriel Stokes, a figure who would come to occupy a pivotal position in the history of both mathematics and physics. Stokes possessed a rare ability to seamlessly bridge the gap between abstract theoretical frameworks and concrete experimental realities. He was equally adept at formulating rigorous mathematical descriptions of physical phenomena and at designing experiments to test the validity of those descriptions. This dual expertise allowed him to make profound contributions to a wide range of scientific disciplines, leaving an indelible mark on our understanding of the natural world. Stokes' journey began with a solid foundation in mathematics. His early education instilled in him a deep appreciation for the power of analytical reasoning. This early training paved the way for his entry into Cambridge University, a centre of intellectual ferment during the Victorian era. Cambridge provided Stokes with an environment conducive to both rigorous study and independent exploration. He quickly distinguished himself as a gifted mathematician, displaying a remarkable aptitude for both pure and applied mathematics. His early mathematical work focused on the intricacies of infinite series and differential equations. These areas, while seemingly abstract, held the key to unlocking a deeper understanding of many physical processes. Infinite series, for example, provided a powerful tool for approximating complex functions and solving equations that defied exact analytical solutions. Differential equations, on the other hand, offered a means of describing the relationships between quantities that change continuously over time or space, making them indispensable for modeling phenomena ranging from the motion of fluids to the propagation of heat. A central challenge in working with infinite series lay in determining their convergence or divergence. A convergent series is one whose sum approaches a finite limit as more and more terms are added, while a divergent series is one whose sum grows without bound. The distinction between convergence and divergence is crucial, as only convergent series can be reliably used to approximate functions or solve equations. Stokes made significant contributions to developing rigorous tests for convergence, providing mathematicians with a more robust toolkit for analyzing these infinite sums. These tests allowed for a more precise determination of when an infinite series could be trusted to yield a meaningful result. His work on differential equations also addressed problems of considerable practical importance. Many physical systems are governed by differential equations that are difficult or impossible to solve analytically. Stokes developed new methods for approximating solutions to these equations, allowing scientists and engineers to gain insights into the behavior of these systems even when exact solutions were unattainable. These approximation techniques proved invaluable in fields such as fluid dynamics, where the governing equations are notoriously complex. The significance of Stokes's early mathematical contributions lies not only in their theoretical elegance, but also in their applicability to real-world problems. He demonstrated a keen awareness of the connection between abstract mathematical concepts and the concrete phenomena they were intended to describe. This focus on practical relevance would become a hallmark of his scientific career. He saw mathematics not as an end in itself, but as a powerful tool for understanding and manipulating the physical world. A pivotal moment in Stokes's career arrived with his appointment as Lucasian Professor of Mathematics at Cambridge University. This prestigious position, once held by Isaac Newton himself, placed Stokes at the very forefront of mathematical research. The Lucasian professorship provided him with the resources and platform to pursue his scientific interests with unparalleled freedom. It also afforded him the opportunity to mentor and inspire generations of students, shaping the course of mathematical and scientific inquiry for decades to come. The professorship was not merely an honorific title. It was an invitation to lead, to innovate, and to push the boundaries of human knowledge. Stokes embraced this challenge with characteristic zeal, embarking on a period of intense research and discovery that would solidify his place as one of the towering figures of 19th century science. His assumption of the Lucasian chair marked a turning point, solidifying his role as a central figure in the scientific community. He brought to the position a rare combination of mathematical rigor, experimental acumen, and a deep commitment to understanding the physical world. This unique blend of talents would enable him to make groundbreaking contributions to fields as diverse as fluid dynamics, optics, and spectral analysis. The problems he tackled were often at the very forefront of scientific inquiry, and his solutions were characterized by their elegance, precision, and lasting impact. Stokes's assumption of the Lucasian chair propelled him into a period of intense scientific investigation, and among the many areas that commanded his attention, fluid dynamics stood out as a particularly fertile ground for his unique blend of theoretical and experimental skills. The movement of objects through fluids, a phenomenon encountered in countless natural and industrial processes, presented a complex puzzle to 19th century scientists. Existing models often fell short in accurately predicting the resistance experienced by bodies moving through viscous media, leaving a significant gap in the understanding of fundamental physical principles. Prior to Stokes' work, the mathematical description of fluid resistance was largely empirical, relying on approximations and ad hoc assumptions that provided limited insight into the underlying physics. While some progress had been made in understanding ideal fluids, those with zero viscosity, the behavior of real fluids, characterized by their internal friction, remained elusive. This limitation posed a significant obstacle in various fields, ranging from naval architecture to the analysis of atmospheric phenomena. The challenge lay in developing a theoretical framework that could accurately capture the interplay between fluid viscosity, object shape, and motion. Stokes tackled this problem with characteristic rigor, focusing specifically on the case of a sphere moving slowly through a viscous fluid. This seemingly simple scenario, he recognized, held the key to unlocking more general principles of fluid dynamics. His approach involved a careful application of the Navier-Stokes equations, a set of non-linear partial differential equations that described the motion of viscous fluids. While a complete analytical solution of these equations remains one of the great unsolved problems in physics, Stokes demonstrated that under certain simplifying assumptions, a tractable solution could be obtained for the case of slow, steady flow around a sphere. These assumptions were crucial to Stokes' success. He assumed that the flow was laminar, meaning that the fluid moved in smooth, parallel layers without turbulence. He further assumed that the Reynolds number, a dimensionless quantity that characterizes the ratio of inertial forces to viscous forces, was small. This condition, known as Stokes' flow or creeping flow, implies that viscous forces dominate over inertial forces, allowing for the neglect of certain nonlinear terms in the Navier-Stokes equations. While these assumptions limited the applicability of his solution to specific regimes, they enabled him to derive a remarkably simple and accurate formula for the drag force on a sphere. Stokes' law, as this formula came to be known, states that the drag force, often denoted as Faf sub d, on a sphere of radius r, moving with velocity v through a fluid of viscosity 8r, is given by F sub d equals 6 pi 8r rv. This elegant equation encapsulates the fundamental relationship between fluid viscosity, object size and velocity in determining the resistance experienced by a sphere moving through a viscous medium. Its simplicity belies its profound implications, providing a cornerstone for understanding a wide range of physical phenomena. The derivation of Stokes' law was a triumph of both mathematical analysis and physical intuition. By carefully simplifying the Navier-Stokes equations and imposing appropriate boundary conditions, Stokes was able to obtain an analytical solution that accurately described the drag force on a sphere in the regime of low Reynolds number flow. This solution not only provided a quantitative prediction of the drag force, but also offered valuable insights into the underlying physics of viscous fluid flow. The formula highlighted the linear dependence of the drag force on the velocity and radius of the sphere, as well as the viscosity of the fluid, revealing the key parameters that govern the resistance experienced by a moving object. The impact of Stokes' law extended far beyond the realm of theoretical fluid dynamics. It found immediate applications in a variety of practical fields, including sedimentation analysis, colloid chemistry, and particle physics. In sedimentation analysis, Stokes' law provided a means of determining the size of small particles suspended in a fluid by measuring their settling velocity. By carefully controlling the fluid viscosity and density, and measuring the time it took for particles to settle a certain distance, scientists could use Stokes' law to calculate the particle radius. This technique proved invaluable in characterizing the size distribution of particles in soils, sediments, and other complex mixtures. Colloid chemistry also benefited greatly from Stokes' law. Colloids, which are mixtures containing particles dispersed in a continuous medium, exhibit a wide range of fascinating properties that are strongly influenced by the size and shape of the dispersed particles. Stokes' law provided a means of estimating the size of colloidal particles, which in turn allowed scientists to better understand the stability and behavior of colloidal systems. For example, Stokes' law could be used to predict the rate at which colloidal particles would aggregate and settle out of suspension, a crucial factor in the design of stable colloidal formulations. In particle physics, Stokes' law played a role in the study of aerosols and other airborne particles. By measuring the drag force on small particles moving through the air, scientists could infer their size and mass, which in turn provided information about their origin and composition. This technique was particularly useful in studying atmospheric pollution and the transport of particulate matter over long distances. The knowledge gained from these studies helped to inform policies aimed at reducing air pollution and protecting public health. Stokes' law also addressed problems in areas such as the behavior of suspensions and emulsions. Suspensions, mixtures of solid particles in a liquid, and emulsions, mixtures of two immiscible liquids, are ubiquitous in both natural and industrial settings. Understanding the stability and flow properties of these complex fluids requires a detailed knowledge of the interactions between the dispersed particles or droplets. Stokes' law provided a starting point for analyzing these interactions, allowing scientists to develop more sophisticated models that could accurately predict the behavior of suspensions and emulsions under a variety of conditions. While Stokes' law is based on certain simplifying assumptions, its enduring relevance stems from its ability to capture the essential physics of viscous fluid flow in a wide range of applications. Its simplicity and accuracy have made it a staple of physics and engineering curricula for generations. Stokes' law continues to be taught as a fundamental concept in introductory courses on fluid mechanics, providing students with a solid foundation for understanding more advanced topics. Furthermore, Stokes' law serves as a building block for more sophisticated models of fluid flow. While it is strictly valid only for low Reynolds number flow around a sphere, it can be extended and generalized to handle more complex geometries and flow conditions. For example, corrections can be applied to account for the effects of inertia at higher Reynolds numbers, or to account for the non-spherical shape of the particles. These extensions build upon the foundation laid by Stokes's original work, demonstrating the enduring legacy of his contributions to fluid dynamics. Even in the age of advanced computational fluid dynamics, Stokes' law retains its value as a benchmark for validating numerical simulations. By comparing the results of simulations with the analytical solution provided by Stokes' law, researchers can assess the accuracy and reliability of their computational models. This is particularly important in the development of new numerical methods and algorithms for simulating complex fluid flows. The analytical solution serves as a ground truth against which numerical results can be compared, ensuring that the simulations are capturing the essential physics of the problem. In modern applications, Stokes' law finds renewed relevance in fields such as microfluidics, where the flow of fluids is confined to channels with dimensions on the order of micrometers. At these small scales, viscous forces dominate over inertial forces, making Stokes' flow a common occurrence. Microfluidic devices are used in a wide range of applications, including drug delivery, chemical synthesis, and biological analysis. Stokes' law provides a valuable tool for designing and optimizing these devices, allowing engineers to predict the flow rates and pressure drops in microchannels with high accuracy. Stokes' law, despite its age, remains a cornerstone of fluid dynamics, a testament to the power of careful analysis and insightful simplification. Its enduring legacy is a reminder that even seemingly simple problems can yield profound insights into the workings of the natural world. The equation continues to inform scientific and engineering endeavors, from the design of microfluidic devices to the analysis of sedimentation processes, solidifying Stokes' place as a giant in the field. Stokes' profound impact extended far beyond the realm of fluid dynamics, illuminating new frontiers in the understanding of light itself. 19th-century optics grappled with fundamental questions about the nature of light and its interaction with matter. Phenomena such as absorption, reflection, and refraction were reasonably well understood, yet the underlying mechanisms remained shrouded in mystery. Scientists sought to unravel the intricacies of how light interacted with various substances, aiming to connect observable properties with the microscopic structure of matter. It was within this context that Stokes embarked on a series of investigations that would revolutionize the field of optics, particularly in the areas of fluorescence and polarization. One of Stokes' most remarkable discoveries was the phenomenon of fluorescence. Prior to his work, the understanding of how certain substances emitted light upon illumination was limited. While phosphorescence, the slow release of light after exposure to radiation, had been known for some time, the instantaneous emission of light at a different wavelength, now known as fluorescence, was a far more subtle and elusive phenomenon. Stokes' meticulous experiments with quinine sulfate provided the crucial breakthrough. He observed that when quinine sulfate solutions were illuminated with ultraviolet light, they emitted a visible blue light. This emission ceased almost immediately upon removal of the ultraviolet source, distinguishing it from phosphorescence. Crucially, Stokes noted that the emitted light invariably had a longer wavelength than the incident light. This observation led him to formulate what is now known as Stokes' law of fluorescence, or the Stokes shift. This law states that the wavelength of fluorescent emission is always greater than the wavelength of the excitation radiation. In simpler terms, the emitted light is always of a lower energy than the absorbed light. Stokes' explanation of this phenomenon involved the idea that the incident light excites the molecules of the fluorescent substance to higher energy levels. These excited molecules then lose some of their energy through vibrational relaxation, a process involving the dissipation of energy as heat. Consequently, when the molecules return to their ground state and emit light, the emitted photons have lower energy and therefore longer wavelength than the absorbed photons. The discovery of fluorescence and the formulation of Stokes' law had a profound impact on various scientific disciplines. It provided a new tool for studying the properties of matter, allowing scientists to probe the energy levels of molecules and to investigate the dynamics of light-matter interactions. Fluorescent spectroscopy quickly became an invaluable technique in chemistry, biology, and medicine, enabling the identification and quantification of various substances with remarkable sensitivity and specificity. Modern applications of fluorescence are ubiquitous. In biomedical research, fluorescent dyes and proteins are used to label cells and molecules, allowing researchers to visualize biological processes in real time. Fluorescence microscopy has become an indispensable tool for studying cellular structures and functions. In environmental monitoring, fluorescence sensors are used to detect pollutants and contaminants in water and air. The principles elucidated by Stokes continue to underpin these diverse applications, demonstrating the enduring relevance of his work. Beyond fluorescence, Stokes made significant contributions to the understanding and characterization of polarized light. Polarization refers to the direction of oscillation of the electric field vector of a light wave. Ordinary light, such as that emitted by the sun or a light bulb, is unpolarized, meaning that the electric field oscillates in all directions perpendicular to the direction of propagation. Polarized light, on the other hand, has its electric field oscillating in a specific direction. The study of polarized light had been ongoing since the early 19th century, with scientists like Etienne Louis Malus and David Brewster making important discoveries about the behavior of light when it interacted with various materials. However, a comprehensive mathematical framework for describing and manipulating polarized light was lacking. Stokes addressed this deficiency by developing what are now known as Stokes parameters. Stokes parameters provide a complete description of the polarization state of light. They consist of four quantities, typically denoted as S0, S1, S2, and S3. S0 represents the total intensity of the light beam. S1 represents the difference in intensity between horizontally and vertically polarized light. S2 represents the difference in intensity between light polarized at plus 45 degrees and minus 45 degrees relative to the horizontal. Finally, S3 represents the difference in intensity between right-hand and left-hand circularly polarized light. These four parameters completely characterize the polarization state of a light beam, allowing scientists to determine whether the light is unpolarized, partially polarized, or completely polarized, and to quantify the degree and direction of polarization. The Stokes parameters can be measured experimentally using a polarimeter, an instrument that measures the intensity of light transmitted through various polarizing elements. The development of Stokes parameters provided a powerful mathematical tool for analyzing and manipulating polarized light. It allowed scientists to predict how polarized light would behave when it interacted with optical elements such as polarizers, retarders, and lenses. It also paved the way for the development of new optical technologies that relied on the control and manipulation of polarization. Stokes formalism also introduced the concept of the Stokes vector, a four-element vector whose components are the Stokes parameters. This vector representation allows for a convenient and concise description of the polarization state of light. Furthermore, Stokes developed the molar calculus, a mathematical framework for describing the effect of optical elements on polarized light. The molar calculus uses 4x4 matrices, known as molar matrices, to represent the transformation of the Stokes vector as light passes through an optical element. The Stokes parameters and the molar calculus have become indispensable tools in modern optical science and engineering. They are used in a wide range of applications, including polarimetry, optical imaging, and remote sensing. Polarimetry is the measurement of the polarization state of light, and it is used to study the properties of materials and surfaces. For example, polarimetry can be used to measure the refractive index and birefringence of materials, to detect stress in transparent objects, and to analyze the composition of surfaces. Optical imaging techniques that utilize polarized light, such as polarization microscopy and optical coherence tomography, provide enhanced contrast and resolution compared to conventional imaging methods. These techniques are used in biomedical imaging to visualize tissue structures and to detect diseases such as cancer. Remote sensing applications of polarized light include atmospheric monitoring and Earth observation. The polarization state of light, reflected from the Earth's surface and atmosphere, contains information about the composition and properties of these media. By measuring the polarization of sunlight, scientists can infer information about the concentration of aerosols, clouds, and other atmospheric constituents. Stokes parameters, therefore, enable a deeper understanding of the world around us, from the microscopic to the macroscopic. The study of light, as it turned out, occupied Stokes throughout his career. His inquiries extended beyond polarization phenomena into the realm of spectral analysis, a burgeoning field in the latter half of the 19th century. Advances in spectroscopy allowed scientists to identify the chemical composition of substances by analyzing the wavelengths of light they emitted or absorbed. Stokes recognized the potential of these techniques and applied his mathematical prowess to develop methods for interpreting spectral data. He investigated the relationship between the spectral lines of elements and their atomic structure, contributing to the growing understanding of the fundamental building blocks of matter. His work in this area dovetailed with that of other prominent physicists and chemists, helping to establish spectroscopy as a cornerstone of analytical chemistry and astrophysics. Stokes also turned his attention to geodesy, the science of measuring and representing the Earth's shape and gravitational field. The determination of the geode, an equipotential surface that approximates mean sea level, was a central problem in geodesy. Stokes tackled this problem with characteristic mathematical ingenuity, deriving what is now known as Stokes' theorem in geodesy. This theorem provides a means of calculating the geode from measurements of gravity anomalies on the Earth's surface. Gravity anomalies are deviations of the actual gravity field from a theoretical reference field, and they reflect variations in the density of the Earth's interior. Stokes' theorem allows geodesists to relate these gravity anomalies to the shape of the geode, providing a powerful tool for mapping the Earth's gravitational field and determining its shape with greater precision. The implications of this work extend beyond pure science, impacting surveying, mapping, and navigation systems. Accurate knowledge of the geode is crucial for determining precise heights above sea level, which is essential for engineering projects, resource management and understanding sea level change. A significant portion of Stokes' later career involved the contentious debate surrounding the nature of the luminiferous ether. This hypothetical medium was proposed to explain the propagation of light waves through space, analogous to how sound waves propagate through air. The wave theory of light, championed by scientists such as Christian Huygens and Thomas Young, had gained considerable acceptance by the mid-19th century. However, the question remained, what was the medium that supported these light waves? The luminiferous ether was invoked as a ubiquitous invisible substance that permeated all space, allowing light to travel from the sun and stars to our eyes. Stokes grappled with the physical properties that such a medium would need to possess. It would have to be incredibly rigid to support the high speeds of light waves, yet also be sufficiently tenuous to allow planets to move through it without significant resistance. These seemingly contradictory requirements led to a variety of theoretical models, each with its own set of problems. Stokes initially proposed that the ether might be a viscous fluid, capable of being dragged along by moving objects. This ether drag hypothesis could explain why the speed of light appeared to be constant, regardless of the Earth's motion. The idea was that the ether in the vicinity of the Earth was carried along with it, effectively eliminating any relative motion between the Earth and the ether. However, this hypothesis faced challenges from astronomical observations. If the ether were completely dragged along by the Earth, it would lead to observable effects on the apparent positions of stars, a phenomenon known as stellar aberration. These effects were not observed to the extent predicted by the complete ether drag hypothesis. Stokes modified his theory to propose that the ether was only partially dragged along by the Earth, with the amount of drag decreasing with distance from the Earth's surface. This partial ether drag hypothesis was more consistent with astronomical observations, but it introduced additional complexities and raised questions about the mechanism by which the ether was dragged. Ultimately, the concept of the luminiferous ether was rendered obsolete by Albert Einstein's theory of special relativity, which demonstrated that light could propagate through a vacuum without the need for any material medium. Despite the eventual demise of the ether theory, Stokes' investigations into its properties were valuable contributions to the understanding of light and its interaction with matter. His work highlighted the difficulties in reconciling classical mechanics with the observed behavior of light, paving the way for the development of new theoretical frameworks. Another area of inquiry for Stokes involved the relationship between gravity and the Earth's shape. He sought to understand how the distribution of mass within the Earth influenced its gravitational field and its overall shape. This involved complex mathematical analysis of potential theory and the application of spherical harmonics to represent the Earth's gravitational field. Stokes' work in this area contributed to the development of more accurate models of the Earth's interior and its gravitational field. These models are essential for a variety of applications, including satellite navigation, geodesy, and geophysics. By carefully analyzing the variations in the Earth's gravitational field, scientists can infer information about the density and composition of the Earth's mantle and core. Stokes' scientific methodology was characterized by a deep commitment to both theoretical rigor and experimental observation. He believed that mathematics should be used to develop theories that could be tested and refined through careful experimentation. This approach is evident in his work on fluid dynamics, optics, and geodesy. He combined his mathematical skills with a keen eye for detail, designing experiments to test his theoretical predictions and to gather empirical data that could inform his models. This emphasis on the interplay between theory and experiment was a hallmark of his scientific approach and contributed significantly to his success. The impact of Stokes' work on subsequent generations of scientists is undeniable. His contributions to fluid dynamics, optics, and mathematics continue to be relevant in modern research. Stokes' law, for example, is still used to calculate the drag force on small objects moving through fluids, with applications ranging from sedimentation analysis to the design of microfluidic devices. His work on polarized light has led to the development of advanced optical imaging techniques used in biomedical research and materials science. His contributions to geodesy have improved our understanding of the Earth's shape and gravitational field, with implications for navigation, surveying, and resource management. Stokes' enduring legacy lies in his ability to connect abstract mathematical concepts with the physical world. He possessed a remarkable talent for translating complex phenomena into mathematical models that could be used to make predictions and gain insights. His work exemplifies the power of mathematics as a tool for understanding and manipulating the natural world. He left a lasting mark on science and technology, with his ideas continuing to influence research and development in a wide range of fields. His work unfolded during a period of unprecedented scientific advancement, witnessing the rise of new disciplines and the refinement of existing ones. Stokes played an active role in shaping this landscape, contributing to the intellectual ferment that characterized the 19th century. His dedication to scientific inquiry, his mathematical prowess, and his commitment to experimental verification earned him a prominent place in the history of science. His influence resonates even today as researchers build upon his foundations, exploring the intricacies of fluid dynamics, the nuances of light, and the mysteries of our planet.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.